OK， 好，开始上课吧。那个，所以这边秀出来，大家看这个那个12个用这个就是你可以讲说其实是用乱数哦，就是说产生出来的这个 image， 对不对？那事实上呢 ，variational autoencoder 可以，应该说这种 generative model 哦，都可以做一些很好玩的事情啊、哦。那我们下面会讲2个，就是说先讲一个，然后后面再讲到另外一个 generative model 的时候，我再讲另外一个好笑的，不说好笑吗？反正也算好笑吧。反正 anyway， 好，那这个我们可以来做什么呢？我们可以来做 semantic interpolation。什么叫 semantic interpolation？ 就是说 interpolation 大家都知道嘛，对不对 ？interpolation 是内插嘛，对啊。Sorry. Okay, I'm supposed to teach English. Okay, I forgot. Okay, yeah, I mean, I need to switch to different mode. Okay, okay. So let me repeat. Okay, so here, okay, you see like 12 different images generated by pretty much like by random numbers, right? So as you can see that variational, actually, the generative model, okay, not necessarily just variational autoencoder, but all generative models can do something very fancy, okay. Later you will see another example that's actually even funnier, okay. But anyway, okay, let's have a look, okay. For example, we can do like for example, the generative model allows us to do what we call semantic interpolation. What is semantic interpolation? You guys know what interpolation is, right? Okay, interpolation basically is just like okay, if you have like A and a B, okay, the interpolation is A plus B divided by 2, right? Okay, very simple idea, right? But this is semantic interpolation. Okay, it's not just interpolation. So what does that mean by semantic interpolation? Okay, so if we directly do interpolation, for example, now, okay, we have these 12 fashion items. If you, for example, say, if you try to generate something in between these two items, then if you directly use interpolation, basically just like the intensity of 1 pixel, of this pixel plus intensity of this pixel divided by 2. So like you do this for all the pixels. Then what you are going to get is like it's kind of like you are putting these two images. Now overlay one image on top of the other. So it's you're going to see like kind of like two images, like stacking up together, but none of them are. Will be clear enough. So it doesn't look like good. Okay. Or for example, you can even do like interpolation with consider if you are doing interpolation with between the shoes and this clothes. This dress. That doesn't make sense, right? That doesn't make sense. But remember, in a previous discussion, actually just in this chapter, we talk about like you could represent like all fashion MNIST data set by two-dimensional points, and you will see like for example some, the items that look similar, kind of clustered together. I know like some of you didn't come to that class. This one. Okay, we talk about you could I mean sort of like a convert each data set, each point in the data set into a point on a two-dimensional space to represent like their relationship, how close an item is from the other fashion item. Okay, so for example, like you can see, because they are all shoes, right? So all these shoes, including the I think this is sandal and high heel, they fall into like this big cluster, and these are the like dresses, and the maybe coat, and the t-shirts here, t-shirt, and pants are here. Okay, so think about this. Okay, if you represent each item, each fashion item, just like a point here. For example, these shoes and these shoes. Okay, you could do an interpolation, like you just add the location of these two places, the point. Okay, the point location that represent these two items. Just add them up, divided by 2, and you could find something in between. And then supposedly you just need to generate something, generate the point like in the middle of those two items, right? Just generate that item back from the point. You need to generate like from this point, generate that. I mean, convert it back to the item, right? So the concept here is called semantic interpolation. So it's basically interpolation, but what we are doing is like we try to find like the point that represents each item, okay, in another space. Okay, and then you do the interpolation in that space, and then try to convert that point back to the item. Okay, that's what we call semantic interpolation. So it's interpolation, but it's interpolated in a different space, and that involves like the transformation from one space to the other. Okay, so here, okay, so let's go back to when we talk about this variation autoencoder. Each instance is represented as a point here, right? Okay, and you could also like get like an interpolation of 2 points, and then use this generative model, this decoder, to generate the middle point back into the item, right? Okay, so that's semantic interpolation. So let me pull you guys back to this the example that we have here. Okay, so now let's assume. Okay, for these 12 items, we want to do the semantic interpolation. What happens is like we want to, for example, like this is 3 by 4, right? 3 by 4. We want to make, change this to 5 by 7. 5 by 7. In our work, we want to, insert 2 rows. We want to insert 2 rows here, and 1, 2, 3 columns in the middle. Okay, so that we want to find the middle, okay, of these 2 items, the middle of these 2 items, the middle of these 2 items, the middle of these 2 items, and so on. Okay? So how do we do it? Okay. Basically, okay, first, we just reshape, okay, this coding size. Okay, remember, like we already have the this one. This is like we obtain this 12 images from this 12 set of codings, right? And these 12 codings are generated randomly, right? So now you see, first we convert this coding, okay, into what we call like a coding grid, but we reshape it into 1, 3, 4, okay, and each one contains a coding size, meaning 2, okay. We have mu and gamma, okay, and then okay, then okay, that was the coding grid, which is represented something like this. We have 3 rows, 4 columns, but now okay, we want to resize it to be 5, 7. When we resize to 5, 7, actually like we will insert 3 columns in the middle and 2 rows in the middle. Okay, so that the original stuff becomes like 5, 7, and this resize function is going to do the interpolation for the codings automatically for us. Okay, remember we are talking about coding. We are not talking about the image. Okay, we are talking about coding. So for each of these, actually it represents 2 random numbers. This is, we have 2 random numbers here, 2 random numbers here, 2 random numbers here, 2 random numbers here, and so on. So once we resize it, okay, we have a new space here, right, in the middle. This new space is going to store, again, 2 numbers. Those 2 numbers will be in the interpolation of these 2 pairs of numbers. We get this, the numbers, in the middle. Okay, so that's like what the reshape is going to do for us. Okay, sorry, resize is going to do us. Okay, and then okay, let me see, and then we just like oh, I'm sorry. This one we just resize it, and then this one we try to get the interpolated result in the middle. Okay, and then after that, okay, we feed this interpolated coding, okay, into the decoder, okay, and to generate the image. Okay, now we have 5, 7, so 35 small images. Okay, compared with the original 12 images. Okay, so something like this, and you can see the ones with the bounding boxes are those who originally we already have in here, but they are stretched. They are separated. Okay, we insert like a new columns and the rows in between the original places, the original column and the rows. Okay, and one thing interesting is that, okay, because these newly created images, they are generated by the interpolated coding, right? They are generated by the interpolated coding. So something very interesting happened. Okay, for example, this is shoes, right? This is another shoes, even though it's not that clear. So these 2 are shoes, right? So the middle one must be a shoes. Same thing. This is shoes. This is shoes. The middle one is a shoes. Okay, shoes, clothes. Well, it's hard to say. Okay, but in between clothes, it must be clothes. In between clothes and pants, it's hard to say. Okay, but okay, clothes, something in between. Okay, they are not generated actually randomly. Okay, because they are generated from the interpolated coding. So they actually represent certain meaning. Okay, in other words, they actually like represent. If we try to, model all these images into the latent space, okay, the middle one will have the same distance to the other, to the the two other codings. Okay, so this is like what we call semantic interpolation. Okay, now so semantic. Oh, sorry. On the other hand, okay, generative adversarial networks. Okay, remember when was variational autoencoder proposed? 2013. Okay, a year after the variational autoencoder was proposed, okay, the GAN, the generative adversarial network, was proposed, okay, by Ian Goodfellow, by their group, okay, and although idea got researchers excited almost instantly, okay, because this is so cool, okay. I mean, you have like two networks, two neural networks fighting together. This idea is brand new, okay. So it took few years. It actually took few years to overcome some of the difficulties of training GAN. So actually, okay, even though the idea was proposed in 2014, but if you still remember, I mean, what I discussed, I mean, earlier about variational autoencoder. I mean, variational autoencoder was proposed in 2013, right? And I told you guys, like, it's popular for a few years, quite a few years. Even now, you can still see like papers, based on the idea of variational autoencoder. But you may ask, like, since GAN was proposed like just a year after the variational autoencoder, why not GAN replace completely all the applications of variational autoencoder? The answer is variational autoencoder is much easier to train than GAN. Okay, GAN is so difficult to train. Actually, the idea, although idea was proposed like 2014, but it took quite a while for the real application of GAN, okay, to come out. Okay. So like many great ideas, it seems simple in hindsight. Okay. So when you look at this idea, it looks simple, but nobody think about this. Okay. Make the neural networks compete against each other. I mean, in the hope that this competition will push them to excel. Okay, so this is like something new. Actually, like I think I also remember seeing another paper which adopt this idea, but they use they try to do something different than GAN. But nowadays, like this idea, I just want you guys to understand this idea to have like a network competing each other is no longer a new idea. But there are other maybe other idea you could somehow borrow from other applications. Obviously, this competition idea is borrowed from maybe game playing, right? Like we guys know, like when we play games, like people, for example, like chess or certain game, like people play like each other, right? And so the idea, okay, maybe like we can find some other idea that may be able to be adopted from other application to neural network. Okay, so I mean the generative adversarial network, okay, contains two parts. Okay, as I said, okay, they compete each other, but the first part is called generator. The second part is called the discriminator. Okay, so generator is going to take a random distribution as input. Okay, normally it's a Gaussian distribution. Okay, it's going to output some data. Normally it's image. Okay, but it's not necessarily image. Okay, because as long as it looks realistic, it doesn't have to be image. Okay, you will see other, but the image will be the probably the easiest like example that you can find for game. Okay, so it's going to convert like some random distribution into image. Don't you feel like this is something that we have just learned, right? In a variational autoencoder, the decoder does just that, right? Right? Okay. So generator offers the same functionalities as the decoder in the variational autoencoder, and it can be used in the same way to generate new images. For example, like to generate like new data to train model. Okay, but it is trained. Okay, the GAN is trained very differently. Okay, we'll discuss like how to train GAN. It's actually a complicated process. Okay, so that's the first part. The second part is discriminator. Discriminator is going to take either a fake image, okay, from the generator or a real image from the training set, okay, as it's the input of discriminator, and it has to guess whether the input image is fake or real. Okay, basically, it's going to have to determine if this image is generated, is artificial one, or it's a realistic photo. Okay, so if we show that into a picture, it's going to be something like that. Okay, here again we are using facial MNIST as an example. Okay, so you can see from the noise. Okay, generator. The goal is to generate like a fake image as good as possible. The goal for the generator is to trick the discriminator into thinking this fake image is a real one. Okay, and the discriminator is going to take either fake image or like a real one. Okay, and the discriminator is going to have to determine the input is fake or real, and the goal of the discriminator is to tell fake images from the real ones. Okay, be able to distinguish these two. Okay, so this kind of looks like police and maybe bad guy who fake like maybe like some people will just try to create like a fake money, right? Okay, so this represents like those bad people who try to create a fake money, and this discriminator is kind of like a policeman or like a bank teller, okay, who has to be able to distinguish the money is real or fake, right? Something like that. So these two roles are competing each other, okay, are competing each other. And of course, like this bad guy become better and better, this guy has to become better and better, right? Otherwise, you know, the economy will have a big problem, right? I mean, the fake money will be all over the world, right? But on the other hand, if the discriminator, if this police is so good, then this, those bad guys also have to improve, you know, on their game, right? Otherwise, they don't survive, right? They don't get they cannot get easy money, right? So, okay, so this is like the basic idea of a generative adversarial network. Okay. So, okay. So during training, generator and discriminator have opposite goals. The discriminator tries to tell fake image from real image, while the generator tries to produce images that look real enough to trick the discriminator. Okay, so they actually they work against each other because the game is composed of two networks with different objectives. So it cannot be trained like a regular neural network. Okay, each training iteration is divided into two phases. So each iteration, we need to train generator and discriminator. Okay, so the training, okay, iteration contains two phases. Okay, so these two phases are like this. Okay, in the first phase, okay, we will train a discriminator. Okay, so a batch of real images, okay, will be sampled from the training set, and is completed with an equal number of fake images produced by the generator. So you may ask, at the very, very beginning, your generator has not been trained at all, right? So it's not going to produce anything meaningful, right? Yeah, but at the same time, the discriminator hasn't been trained either, right? So you know, how does it do the job? That's very interesting, okay? So we label 0 for fake image and 1 for real image, okay? And the discriminator is trained on this labeled batch for one step, okay? So I mean, for the first phase, okay, we train the discriminator, okay, from this batch for one step using the binary cross entropy loss. Why is it binary cross entropy? Because we are telling the input image is fake or real, so it's a binary classification, right? It's a binary classification, so we use binary cross entropy as the loss function. Okay, so importantly, backpropagation only optimizes the weights of the discriminator during this phase. So we actually freeze the generator. We don't tune the weights for the generator at all. Okay, so in the second phase, we train the generator. Okay, so we will use the generator to produce another batch of fake images, and once again, okay, the discriminator is used to tell whether the images are fake or real. But this time, okay, we do not add real images. Okay, we use all the images we use are fake ones, but we label them. We label these fake images ground truth as 1. We label this fake image ground truth as 1. Okay, so we want the generator to produce images that the discriminator will believe to be real. Okay, so crucially, the weights of discriminator are frozen. Okay, so in this phase, the discriminator weights will be frozen, but the generator weights will be unfrozen. Okay, so backpropagation only affects the weights of the generator. So think about this. Okay, when you produce the output and you try to compare the output with the ground truth, which is 1, right? Okay, in this phase, okay, the ground truth is 1, right? But the input is a fake image, right? Okay, so it will tell, so in the backpropagation, it's going to tell well, because discriminator weights are frozen, right? So, but you can only change the generator. So it's going to tell the generator, you know, the difference between this fake image and the ground and the real image. Okay, and that gradient is going to be used to somehow like you know, tell the generator to do a better job, in generating the image next time. Okay, so this is very interesting. Okay, and the generator, okay, this is very important. The generator never actually sees any real images, but it gradually learns to produce convincing fake image. It never sees the real image, but it still learns how to generate fake image better and better. Okay, all the generator gets is the gradients, you know, flowing back through the discriminator. Okay, so the better the discriminator gets, the more information about the real images is contained in these second-hand gradients. So the generator can make significant progress. So this is very interesting. The generator never actually see the real image. Okay, the generator actually try to improve itself through the discriminator. Okay. Well, it's a break time again. Let's take a 10 minutes break, and then when we come back, we'll see this example. Okay.
对
Okay, sorry, was discussing with other professor about the proposal. Okay, so so we just discussed about the game, right? So let's have a look at this example of a game, Profession MNIST. Okay, so you can see here the generator, okay, looks very similar to the decoder in the variation autoencoder. Okay, you can see. Okay, coding size is 30. Okay, and the generator. Okay, we use sequential API, so we have a dense layer. Okay, with 100 neuron with zero activation. Okay, and we use the coding size as the input shape. Okay. And then we have 150 neuron for the next layer, zero activation. And then, okay, remember this is generator, right? So the final result is to generate the image. Okay, so we use the dense layer. Okay, this okay to generate the 28 by 28. Okay, neurons and using the sigmoid activation. Okay, the reason to use sigmoid activation is the same as the what we talked about previously, okay, because we treat each pixel as a binary classifier, okay, so we use sigmoid, okay, and then we reshape it into two-dimensional, okay, 28 by 28, so that's generator, very simple. And the discriminator, it's a very simple binary classifier, okay, it takes the image, okay, and then it outputs like it's a binary classifier to determine this image is a real or fake. So it first take the 28 by 28 image and flatten that, and then okay, we feed that to 150 neuron dense layer with zero activation, another 100 neuron dense layer with zero activation, and last one. Okay, we have one neuron, okay, using sigmoid. Okay, the reason is because, again, okay, it's a binary classifier. Okay, we want to tell this image is fake or real. Okay, so well, we only need one neuron, and sigmoid will output like a probability that this image is real. Okay, and then we put these two generator and discriminator together to form a GAN model. Okay, so it's sequential. Okay, generator, discriminator. We put them together. First, I would like to point out. Okay, that the generator and discriminator. I mean, remember this is GAN. Okay, this is the generative adversarial network. So this is no longer autoencoder. Okay, so because this is no longer autoencoder, so the generator and the discriminator do not need to be symmetric. Okay, do not need to be symmetric. They have different purposes. Okay, even though in this example, okay, you see 100 neuron, 150 neuron, 150 neuron, 100 neuron. They look a little bit like they are symmetric. but they don't have to be symmetric. Okay, they don't have to be symmetric. Okay, I just want to point that out. Okay, and then okay, after that we need to compile this model. Okay, so the discriminator is binary classified, so we can just use the binary cross entropy loss. Okay, generator will only be trained through the GAN model, so we do not need to compile the generator at all. Okay, and the GAN model is also a binary classifier. Okay, because it's like we try to get the output of the discriminator and and compare with the label, and then the gradient will flow back. I mean, in the back propagation will flow back to the generator. Okay, so this is like we don't directly train the generator. Okay, but the GAN model is also using the binary classifier. Okay, so the discriminator should not be trained during the second phase. So we make it non-trainable before compiling the GAN model. So it's going to be something like this. Discriminator compile, okay? We compile discriminator, okay? Loss is binary cross entropy, optimizer, Armis prop, okay? So as you can see, like I mentioned earlier, okay? For some reason, okay, the generative model normally use Armis prop more often than the other optimizers, okay? So after this compilation, okay, we set the discriminator trainable to be false, and then we compile again. Okay, so GAN compile, okay, is again used by binary cross entropy, and optimizer still use Armis prop. So the trainable attribute, okay, is taken account, okay, only when compiling a model. So in a GAN, okay, discriminator, discriminator weights are frozen because we set this before we compile the GAN model. We set discriminator to be, trainable to be false. Okay, so when you train again, okay, discriminator weight is frozen. Okay, but when you train discriminator directly, because we did not, freeze the discriminator weights before compiling the discriminator. So discriminator, when we train the discriminator, the discriminator weights are trainable. So this is a little bit special. I just want to point out that to you guys. Okay. And then we need to prepare the data. Okay. So first, the batch size is 32. Okay. So we get the data set. And then we do the shuffling. Okay. And I think that's like not too much to talk about. But now, okay, the training loop is is something special in GAN. Okay, because as I mentioned, the GAN has two phases. In the first phase, we train the discriminator. In the second phase, we train the generator through the GAN. Okay, through the GAN. We do not directly train the generator, but we train the generator through the GAN. Okay, so you can see, okay, here, okay, we define this train GAN, okay, function, and we pass the GAN model, data set, batch size, coding size, okay, default number of epochs to be 50, okay, so and then we loop this for n epochs time, okay, default to be 50, okay. So for X batch in data set, okay, so here, okay, this part is phase 1. The second phase is here, okay. The first phase, okay, noise, okay. We first try to get the random numbers, okay, and use that as the coding to generate the fake image. Remember, the first phase, we are going to use half fake image, half real image, and then use that as a training set, as a one batch of a training set to train the discriminator. Okay, so we get the noise first, and then we put the noise into the generator to generate the images. Okay, and then we try to put this fake generated image with the real image together. Okay, and then here we try to assign the label to the image properly. Okay, the first half to be fake image, so their label will be 0. The second half of the batch will be the real image, so the label will be 1. Okay, and then here we set discriminator.trainable to be true. The reason to have this, this line is not needed. Okay, it's not needed. I mean, supposedly discriminator weights are not frozen here. Okay, because we call discriminator train on batch. Okay, and we use this fake and real data set and use this ground truth to train the discriminator for one batch. But as I already told you, discriminator weights are not frozen. Okay, so you may ask, why do we need to especially set this line to be true? It is because, well, the TensorFlow, when you see that, here, after you compile it, because at some point in time in your program you set discriminator trainable to be false, right? Even though this is for the game model, this is not for this discriminator model, but when you try to, modify the discriminator weight here, it's going to produce some warning message. This is not going to be an issue. You can ignore the warning message, but if you do not want to see those warning message, you could, like here, explicitly, add a line like this, just to tell, the TensorFlow, this is not an issue. We intentionally want to modify the weight in the discriminator model. So again, let me repeat. Without this line, everything works just fine. It's just like the TensorFlow is going to produce a warning message because the TensorFlow will see some point in time you said the discriminator trainable to be false. So it's going to question, maybe you don't want the discriminator weight to be modified. So it's going to, show you some warning messages, just to remind you, do you want that or not? But since we do want that, we do want to modify the weights in the discriminator. So we, if you want to suppress the warning message, you add this line. And then so the first phase, as I said, you train the discriminator on this batch. And then in the second phase, we train the GAN. And when we train again, you can see, noise. Again, we try to generate certain noise, but this time we try to generate all the fake images. So we try to, because, and we intentionally set the ground truth to be 1. And then, now we set the discriminator weight to be false. Because in this game model, we already set discriminator trainable to be false. But again, because here you set discriminator trainable to be true, right? So here, okay, it's going to ask you, okay, because again, I mean, without this line, everything works fine, okay? Because you are training the GAN. When you train the GAN, okay, because before you compile again, okay, you already set the discriminator trainable to be false. So the discriminator weight will be frozen, okay, when you train again. But it's just like again, okay, because you know the TensorFlow sees that at some point you set discriminator trainable to be false, right? Sorry, to be true. So it's going to ask you. It's going to generate warning message just to remind you, okay, are you going to freeze the weights of discriminator in the GAN model or not? Okay. So again, to suppress that warning message, you just add a line here so that it will not produce the warning message. Okay, and then you use GAN train on batch. Okay, this one. Okay, and that's it. Okay. Okay. So I think I already explained like pretty much everything. Okay. So so it looks nice, right? It looks nice. Okay. That's it. Okay. If you display the generated image, okay, you will see that at the end of the first epoch, okay, at the end of first epoch, they already start to look like facial MNIST image. Okay, so it's going to be something like this. Think about this. This is like the end of the first epoch. The generator already picked up some information on how to generate the facial MNIST data set, obviously, right? Okay, but unfortunately, okay, these images never really get much better than that. You may even find epoch where the GAN seems to be forgetting what it learned. Okay, so why is that? Okay, so actually, you know, training GAN is very difficult. Okay, you know, why is that? Let's discuss. Okay, so the issue is like this. Okay, during training, generator and discriminator will try to compete each other. We know that, right? So this is, I mean when two entities compete each other, we call this a zero-sum game. Okay, it's kind of like our situation with China. Okay, it's a zero-sum game. Okay, some people call it that way. Okay, so as training advances, the game may end up in a state that game theories called Nash equilibrium. I don't know if you know about this. Okay, Nash equilibrium. Okay, Nash equilibrium. This is named after a guy called John Nash. Okay, this is a genius. I mean, I don't know if you have watched the movie. There's a movie called A Beautiful Mind. Maybe like about 10 years ago. Okay, or even longer than that. Okay, the actor, I think, who is the actor? The actor is the guy who played the gladiator. I forgot the name. Do you guys remember the name? Huh? Russell Crowe. Cohen. Yeah, Russell Cohen. I mean, he's very good. Okay, of course, he's a very good actor. But the important thing is that, I mean, if you watch that movie, okay, you will learn the real story about John Nash. Okay, that movie is a very this John Nash is a. Have I ever talked about this guy in this class? No? Okay. I mean, yeah, I think I talked about him like in another, probably in another class. But anyway, I mean, this guy is obviously a genius, okay, and he entered Princeton, okay, to study for his PhD, okay. I think he only, you know, the thing is not about like his it's not about like how much time he I mean he spent to get his PhD. The thing about special about him is how many pages he wrote in his PhD thesis. I remember he only wrote like maybe 5 or 6 pages, okay, in his PhD dissertation. You can Google on his name, okay, on Wikipedia. I think it will mention his thesis. I mean, because you know, it's not any school. It's Princeton. Come on, it's Princeton, and the math department. I mean, nobody will let you go, okay, with you know with just any 5-page math PhD thesis. Okay, that's just you know, because in that thesis, okay, in that dissertation, he actually proposed this Nash equilibrium. Okay, this Nash equilibrium. Okay, I think when he proposed that, he was like maybe 25, 26. Okay, very young. Okay, and because that has a very deep, you know, impact. Okay, he went to MIT to be a professor there, but later because he went crazy. Okay, I think if you watch the movie, you'll know that. I mean, because he was kind of paranoia. Okay, a lot of like probably a lot of like genius are crazy people, you know. So that's why sometimes I mean I'm glad I'm not a genius, you know. I mean, you know, I'm normal, okay. But this guy, okay, I mean, this Nash equilibrium, okay, after another 30 years, it earned him economics Nobel Prize. Okay, because at the time when he proposed that, okay, even though in mathematics field, people understand his contribution, but it was not until 30 years later that concept became so important in economics that you know, the Nobel Prize, you know, decided to give him this Nobel award. Okay, so when he received the award, he was just, I think he was just recovered from his illness. Okay, and so that was a kind of touching moment, you know. So it's actually like a very interesting movie to see. Okay, so the important thing about the Nash equilibrium is okay, in a zero-sum game, when two parties compete each other, okay, there's a certain state which is called this Nash equilibrium that no one wants to change. Okay, this is assuming if two sides are trying to use the best strategy, then you will find that, you know, nobody would like to change the state. Okay, that state is called this Nash equilibrium. Okay, so an example is like this. Okay, we know in Taiwan, everybody drive on the right hand side, right? Okay, so this is a Nash equilibrium. Everybody drive on right hand side. If you decide, if you, in particular, just you, decide, I don't want to drive on the right hand side, I want to change this strategy, what happens? You'll get killed, right? Because you drive on the other side, so accident happens and you lost your life, right? Okay, so this is an example. Of course, it doesn't mean like there's only one Nash equilibrium state. Okay, obviously there's another state like everyone drive on the left-hand side, which is also fine, right? Okay, so as for like this game, whether or not this game, I mean, I'm talking about like which side to take on driving. Okay, it is converged to everyone drive on the right-hand side or everyone drive on the left-hand side. It depends on the initial condition. Okay, but basically, okay, when this equilibrium is reached, nobody would like to change that. That is why, okay, you will not see a country. You will not see a country that has like the rule like okay, we can drive on the left-hand side and the right-hand side. Okay, no country will do that. Okay, I heard that there's a special situation. I think in Hong Kong, because Hong Kong people drive on the left-hand side. Okay, but China. In China, people are driving on the right-hand side. But Hong Kong and China are sort of connected together, right? And Hong Kong has been reunified with China, right? So when Hong Kong car somehow gets into the China, they need to switch to the right-hand side. Okay, from the left-hand side to the right-hand side. There's a point, okay, where all the cars have to change the rule. Okay. Without that, obviously there will be a lot of traffic accidents, right? So that's a very interesting example. Okay. So different initial states and dynamics may lead to one equilibrium or the other. Okay. So there in this example there's a single optimal strategy. Okay. Once the equilibrium is reached. Okay. Why do we say a single optimal strategy? I mean like driving on the same side. Okay, I mean as for whether it's left-hand side or right-hand side, it's determined by the initial state and dynamics. Okay, but as Nash equilibrium can involve multiple competing strategies. Okay, for example, like a predator chases its prey, the prey tries to escape. Neither would be better off changing their strategy. Okay. The predator has to chase the prey, otherwise you will be starving to death, right? But prey has to run from the predator, otherwise it will be eaten. Right? So basically, no one wants to change their strategy, right? So this is like another example, So there's a lot of such a situation. Okay, so how does this apply to games? Okay, because there's a paper. Okay, I'm sorry. I mean I didn't include the link. Okay, but in the slide. But basically there's a paper that demonstrates a game can only reach a single Nash equilibrium. Okay, that's when the generator produces perfectly realistic images. And the discriminator is forced to guess. Okay, in this case, I mean forced to guess just the discriminator basically cannot be able to identify the input image is real or fake. So it can only guess. Okay, 50% real, 50% fake, because other than it cannot do anything better than that. So this fact is very encouraging, right? So it looks like if we train again enough amount of time, okay, it will eventually reach this equilibrium, okay, ideally speaking. So it will give you perfect generator. Okay, unfortunately, this is not the case. Okay, nothing guarantees that equilibrium will ever be reached. Why is that? Okay, there's a issue called mode collapse. Okay, mode collapse. Okay, this is the biggest difficulty in GAN training. Okay. What is mode collapse? It is when generator output gradually become less diverse. Okay. Why the generator's output will become less diverse? Okay. Suppose the generator gets better at producing convincing shoes than any other class. Okay, just a little bit, just a little bit. Okay, here I'm not saying like a lot, just a little bit. Okay, it becomes better at one particular category. Okay, by just a little bit. So it will fool the discriminator a little more with shoes. Okay, because it can generate shoes better, right? So this will encourage the generator to produce even more images of shoes, right? Because, after all, in a deep learning, okay, the network, you sort of can consider a network. It's just like a human, okay? It can try to find like the best strategy because it wants to fool the discriminator, right? And once it finds that generating shoes give it advantage in fooling the discriminator, then what happens is that, okay, so the discriminator will produce more image of shoes. Okay, so gradually you'll forget how to produce anything else because your generator will generate more and more shoes image. Okay, and then eventually you'll forget to generate other type of image, and at the same time, because only fake images the discriminator will see will be shoes, right? So discriminator will also forget how to discriminate fake images of other classes. Okay, and eventually, when discriminator manages to discriminate the fake shoes from the real one, okay, the generator will be forced to move to another class, right? So you have to be forced to move to other classes. For example, from shoes to shirts. Okay, so it may then become good at shirts, forgetting about shoes. Okay, and the discriminator will follow. So this is kind of like you will find that generator is getting better at one class and nothing else, and discriminator will also become better at discriminating a particular class. But then, okay, when discriminator catch up the generator, okay, in terms of that class, okay, then what happens? Generator will go to another class, and then, this thing will, happen, iteratively. So the game may gradually cycle across a few classes, never really becoming very good at any of them, okay, because, it's not going to settle down and then, be able to generate all the images very well. Well, unfortunately, this is not the case. Mode collapse. So, moreover, because generator and discriminator are constantly pushing against each other, so their parameters may end up escalating and becoming unstable. So, because it's a they are very, very sensitive. Okay, because they are this kind of like competition is like is a dynamic changing, right? So you will find that, okay, training may begin properly, then suddenly diverge for no apparent reason due to the instabilities. So since many factors affect this complex dynamics, so GANs are very sensitive to hyperparameters. So you may have to spend a lot of time fine-tuning the hyperparameters. So this is the issue with the GAN, okay, especially the GAN training. Okay, so there are some ways to fight with the this mode collapse. One way to do it is, okay, instead of getting fake image directly from generator and then use that for discriminator to tell which one is real, which one is fake. Okay, we maintain a buffer. Okay,